Solution: a homogeneous mixture of two or more substances. Examples of solution is perfume, juice, and shampoo. Those are examples of simple solutions. Moving on to miscible and polar. Miscible, a term describing two liquids that are soluble in each other. An example of that is water and salt. Simply take the salt, pour it into the water, and stir. They most definitely mix. Polar, having unequally distributed electrical charges, which is another example of this. Moving on over here to immiscible and nonpolar. Immiscible, a term describing two liquids that are not soluble in each other. An example of that is water and olive oil. Simply take the olive oil, pour into the water, take a spoon, and stir. They do not mix whatsoever. Nonpolar are compounds that do not dissociate into ions, which is also an example of oil and water. If you move over here, here's a chart that simply breaks down polar, nonpolar, immiscible, and miscible. If you have a polar and polar, they equal miscible. If you have polar and nonpolar, they equal immiscible. Nonpolar and polar also immiscible, and nonpolar equal miscible. Moving on to dissociation. Dissociation is the process in which a process disrupts the attractive forces in a solute and pulls the solids apart. An example is this Sweet Baby Ray's mint sauce I have. If you look very closely, you can tell that the solutions have kind of pulled apart.
Dilution. Adding more solvent to a solution so the concentration of the solute becomes lower. So we have a cup of milk and a half a cup of water. The water was the solution. The solvent was the milk. And the water being less, the milk overpowered it to make the solute become lower. Then we go to concentrated solution. We have a tablespoon, a tablespoon of water and a tablespoon of sugar. Mix that, which makes that an equal ratio of solute to solvent. Molality. A quantitative measure of a concentration equal to the number of moles of a solute per kilogram of solvent. M equals moles solute divided by kilogram solvent. Molality. No, molarity. A quantitative measure of concentration equal to the number of moles of solute per liter. Molarity is a measure of concentration. 1 mole equals 6.22 times 10 to the 23rd power. Example of molarity would be 2 moles of a solute dissolved into 1 liter of a solution. You take the 2 moles divided by the 1 liter, which equals 2 molarity. Another example would be 58.44 grams of NaCl, and you dissolve it into exactly 2.00 liters of solution. First step, convert grams to moles, so 58.44 grams divided by 58.44 grams over moles equals 1 mole. 2. Divide moles by liters to get molality. 1 mole divided by 2 liters equals 0.55 mole over liter. Finding the molality is harder because you can't use actual numbers like in molarity. You're using chemical because you have to use chemicals. So you do the grams over the molar mass equals the moles. Then you take the moles over the volume and you get the molality.
Boiling point elevation. The effect that solute particles have on boiling points of substances is boiling point elevation. The Molar boiling point elevation constant, capital K, lowercase b, and p, is 1 mole of particles into 1 kilogram of water. The chemical equation for molar boiling point elevation is listed below. As Rough Law states, the lowering of the vapor pressure of a solvent is directly proportional to the number of solute particles. As listed below on the chart is the boiling point elevation of these following solvents: acetic acid, acetone, benzene, carbon tetras, ethanol, ether, phenol, and water. The change in freezing point is called the freezing point depression. It is represented by delta, capital T, lowercase b, lowercase p. As with molar boiling point elevations, constants, each solvent has its own characteristics. Molar freezing point depression constant is represented by the following: capital K, lowercase b, lowercase p. In this chart listed, these are the freezing point depressions of solvents: acetic acid, benzene, ether, ferro, and water. All of these solvents has a point depression change. Osmosis. The process in which water moves across a selectively permeable membrane. One example of osmosis is carbon dioxide moving into the leaf cells of a plant. Another example of osmosis is oxygen moving into the bloodstream. And the third example for osmosis is water moving into the root
In this
cells of a
experiment, we will
plant.
be demonstrating the Tyndall effect. A solution is a homogeneous mixture, uniform throughout. It stays the same, particles mix completely, and it contains a solute and a solvent, small particles. You know it's a solution when the light shines through. You don't see anything floating, it's mixed completely. Move on to the colloids. A colloid is a homogeneous mixture, uniform throughout, except when we leave it alone for a long time. The particles are medium sized. When you shine the light through, you can see the particles moving. Like if you stir it and let it sit, you can see the oil and the water not mixing together. It sits on the top. If you move on to suspension, it's a heterogeneous mixture, not uniform throughout. It has layers, and it has large particles. This is mayonnaise in water. If you shine, the light does not shine through. You can't see through, and it forms layers. That is the top layer and the bottom layer.